Hello, my name is Pete Melvin, and this is a video about limits using graphs and tables. First off, what is a limit? Well, in calculus terms, a limit basically means when the input is really close to a certain value, A, then what is the output really close to? More practically, we tend to think of limits in the context of as x approaches an input A, what are the y values or outputs of the function approaching? We've actually already encountered limits in this course. In our previous topic, we looked at two applications of limits. We looked at the slopes of secant lines as one input got closer and closer to another input. And we saw that the outputs of the difference quotient, change in y over change in x, was approaching a specific number, the slope of the tangent line. We also saw when we took the average velocity over a time interval from t1 to t2, as that time interval got closer and closer to zero, we looked at what the values of the average velocity we're approaching. We said that as the time value approaches zero, the average velocity is approaching the instantaneous velocity of the object. So those are two applications of limits. They're really kind of the same application of limits. They're both rates of change. And that is the main use of limits that we will have in this course, Calculus 1. But there are other uses of limits and other applications. And so before we devote our focus to rates of change as a main application of limits, we are going to look at other uses of limits and also different techniques for evaluating and understanding limits. So we're going to start off by looking at a more general, simpler application of limits. Let's look at this example here. We have a function, f of x equals x squared minus 2x minus 3 over x minus 3. What happens to this function at x equals 3? Now, we should probably be able to very quickly see that when x is 3, this function is undefined. Right? Quite clearly, f of 3, we get 3 minus 3 on the bottom, which means we get something over 0. And in a certain sense, it doesn't matter what happens on the top. If the denominator is 0, the value is undefined, and that is true. However, sometimes, even though the function is undefined, we still want to figure out what's happening in the numerator, as we'll see in just a second. So let's plug in 3 to the top. And so we get 3 squared minus 2 times 3 minus 3, which is, of course, 9 minus 6 minus 3, which is 0. Now, you might recall from pre-calculus, this is a rational function. And in pre-calculus, we learned that rational functions have certain behaviors in certain situations. Specifically, rational functions often have vertical asymptotes. And those occur when at inputs that make the denominator 0 and make the numerator something that's not 0. We also know that rational functions sometimes have holes. Those occur when the input makes the denominator and the numerator both 0, which is what is clearly happening here. So it is important to note that this function does not have a vertical asymptote when x equals 3. This function has a hole when x equals 3. In fact, we can look at the graph and we can see, yep, there's a hole right there at x equals 3. Now, I want to know right now what happens as x approaches 3 from the left. Something happens. What happens? Well, let's find out. Graphically, we can look at this. We can say, okay, well, here's x equals 3. Let's mark it on our x-axis. And as our x values get closer and closer to 3 from the left side, we can see that those x values correspond to these points on the graph that are approaching this specific point, and that corresponds to specific y values that appear to be approaching a specific y value on the y-axis, namely 4. So as x approaches 3 from the left, y approaches 4. We can also see it from the right side, that as x approaches 3 from the right, well, let's see. As x approaches 3 from the right side on the x-axis, that corresponds to these points on the graph, which are, again, approaching the same point. And on the y-axis, they're approaching y equals 4. So y is approaching 4. Now, we call this a limit. Really, it's the limit of the function. The limit of f of x as x approaches 3 is 4. And we have notation for that. We say limit, and I use a script L for my limits. Some people use a capital L. I don't like using my regular handwriting lowercase l because it looks like a 1. But anyway, limit, and underneath that we write x arrow 3, meaning x approaches 3 of f of x. And we say that is equal to 4. So that is the notation to say the limit of f of x as x approaches 3 is equal to 4. Or you could say the limit as x approaches 3 of f of x is equal to 4. And again, going back to my earlier informal definition of limits, what this is saying is that as x gets closer and closer and closer to 3, the y values get closer and closer and closer, or the outputs of the function get closer and closer and closer to 4. Now, of course, we can see from this graph, since it has a hole there, the function never gets to a y-coordinate of 4. The x values, when x gets to 3, the function doesn't exist. F of 3 does not exist. But as x is approaching 3, the y values are still approaching a specific number. They never get there, but they are approaching that value. Now, if you'll indulge me in an imperfect analogy here, right? Sometimes the journey is more important than the destination, right? And we've all heard that phrase before. It is not a perfect analogy, but that's kind of what's going on here, is that we're not just interested in where we end up. We often are, that's often very important, but that's not always the only thing that matters. Sometimes we are equally or even more interested in where we're headed, right? Even if we don't get to where we're headed. To use another imperfect analogy, sometimes we set out to do something and we don't accomplish what we tried to accomplish. Right? We make a mistake, or we encounter a variable that we were not expecting. May be our fault, may not be our fault, but we don't always achieve what we were hoping to achieve. The outcome is not always the outcome we were attempting to get. And in a lot of cases, we are interested not only in what happened, but also what was going to happen, what should have happened, what were we trying to achieve. Again, not a perfect analogy, but in the world of calculus, we are very, very often interested in what the values are approaching, whether or not they get there, right? Another thing that you can do with this graph is you can say, let's just pretend that we black this out. And we didn't know that there was a hole there. And we just said, okay, well, ignoring what actually does or does not happen at x equals 3, what do we think, what does it look like should be happening when x is 3? Well, based on, if we look at everything to the left of 3 and everything to the right of 3, what do we think the y value would be when x is 3? And we can see from both sides, as x approaches 3, the y value is approaching 4. The fact that it never gets there is a different issue, a different question. Okay, so that is a graphical approach to limits. We can also evaluate limits numerically using a table. So we can say, okay, let's plug in some numbers here. Let's make a table. Let's say we want to know what happens when x is 2.8, and we plug 2.8 into the function. And so I'll get my calculator here. Oh, let me actually write down the function here. The function was x squared minus 2x minus 3 over x minus 3. Let me double check that real quick. Minus 2x minus 3. Yep, that is our function. And we can evaluate that. What is f of 2.8? So I'll get my calculator, and we'll say, over there, 2.8 squared minus 2 times 2.8 minus 3. That's what we get in our numerator. Divide that by parentheses 2.8 minus 3. And we get 3.8. Let's do it again. Let's get a little closer to 3, say 2.9. Again, we'll plug it into our calculator. 2.9 squared minus 2 times 2.9 minus 3 divided by parentheses 2.9 minus 3. And I get 3.9. And we could plug in 2.99. Okay, 2.99 squared. Oops. Squared, there we go. Minus 2 times 2.99 minus 3 divided by parentheses 2.99 minus 3. And we get 3.99. Now, you might notice there's a pretty obvious pattern in this case. Right? Pretty clearly, well, it looks like we're just taking this x value and we're adding 1 to it. Yes, the patterns will not always be obvious, but we are in fact looking for patterns. Right? We are looking for a pattern. And we see a pattern here, and so it's okay. It's good to recognize a pattern. It's important for us to realize that patterns don't always work out the way we think they do. So we do need to be careful when we think we see a pattern. It may not be doing what we think it's doing, but in this case, for the sake of time and simplicity, I will verify that yes, the pattern that you think you see really is the pattern. So I could say, oh, 2.9999, that's 3.9999, and so on. We can get as close as we want to 3. And we can see that the closer and closer we get to x equals 3, the closer and closer the outputs get to 4. And we can look at this from the other side as well. And we could say, okay, let's plug in some values of x to the right of 3 or larger than 3, like say 3.3 and 3.2 and 3.1 and 3.01 and 3.001 and so on. And we can get as close as we want. For the sake of time here, I'll work out the first one. 3.3 squared minus 2 times 3.3. Nope, I made a typo there. Let's try that over again. 3.3 squared minus 2 times 3.3 minus 3. We divide that by parentheses 3.3 minus 3. And we do get 4.3. I won't make you sit here and watch me calculate all of these. You are free to pause the video and work them out yourself if you want to. But we do get 4.2 there, and 4.1 there, and 4.01 there, and 4.001. Again, feel free to pause the video and work those out yourself, but that is what we get. And so once again, we see numerically, or with the table of values, the limit as x approaches 3 of f of x is 4. So there we go. We have evaluated this limit graphically and numerically. Now it is very important to point out that both of these methods are approximations, right? Table of values allows us to be very, very precise, but it is still just an approximation, right? Again, it's a very obvious pattern in this case, but our functions, our expressions are not always leading to simple integer or even rational values, right? Sometimes we're dealing with functions that have square roots in them, or trig functions or exponential functions or logs, right? So we cannot always assume that we're approaching a nice round number. In this case, pretty obviously approaching 4. But sometimes the thing that they're approaching is actually the square root of 17. And you're not going to recognize the square root of 17 with a table of values like this, right? So there are limitations to using a table of values. There are also limitations to using a graphical approach, because even though it's pretty obvious from this graph that those y values are about 4, maybe I'm giving you a trick question here, and maybe the exact coordinates of this hole are actually 3, 4.005, right? They're not. It really is 4 in this case, but they could be. Sometimes they will be, right? So we need to be careful and remember that anytime we use a graph or a table of values to evaluate a limit, at best, we are approximating the value of that limit. Sometimes that's the best we can do, and sometimes that's good enough. But there are other times when we really want to know an exact value. We want to be able to prove and verify that it is a certain exact value. For that, we need other more precise techniques for evaluating limits, which we will do in our next video.